Hello everyone. In this lesson we're going to take a look at sound waves. Sound waves are a mechanical wave, so they exhibit all the behaviors that we've seen. They do require a medium, but we're very familiar with them because we use them every day to communicate. So, some properties of sound waves. First, sound is a longitudinal wave, and that means it consists of a series of compressions and rarefactions. And this should make sense to you. If you've ever watched a speaker vibrate, you know the speaker moves back and forth this way. We have a speaker, right? And that causes compressions and rarefactions in the air, and they travel through that, and then our ear detects that, and we hear sound. So compressions and rarefactions, which means it can actually travel through anything, solid, a liquid, or a gas, each at different speeds. Transverse waves, remember, they can't travel through liquids or gases. They can only travel through solids, but a longitudinal wave can travel through anything. Now, in air, sound travels about 343 meters per second, which we think is pretty fast, but it's even faster in liquids and it's fastest in solids because in solids those particles are closer to each other, and so a compression is more able to travel through it. It's a quicker domino effect, I suppose. One particle immediately hits the next particle in a solid, so the sound wave travels much faster. Okay. The pitch of a sound wave is determined by the frequency of the wave. And you guys are probably familiar with this too. You know the tuba is a big, long instrument and it plays a very low note. And the bigger the instrument, the longer the sound wave that can fit in it. So sound is a longitudinal wave, not a transverse wave, but I'm going to draw it like this. This is a very long wave. It would fit in a very long instrument. But a shorter wave is going to occur more frequently, and that's going to be a higher pitch. You can get many more waves in there. If it's a shorter wavelength, then you're going to get a higher frequency, which means a higher pitch. So musical instrument size can give you a pretty good idea of the pitch that it's going to make. Smaller instruments, higher pitch because it's a shorter wavelength. Bigger instruments, lower pitch because it's a longer wavelength. Okay. We can detect sounds between about 20 and 20,000 hertz, although as we age, this number gets lower. So there used to be a ringtone that was pretty popular that kids would download, and it was like, you can only hear this if you're under 25. And it was just a very high-pitched frequency. There's ultrasonic frequencies, which are above this, that we can't hear, but we can use them. Like the motion detectors you guys have used in class send out an ultrasonic pulse. Okay? The Doppler effect we've looked at before. And this is an animation of a sound wave that's being created by this source at the middle. So this source is vibrating at a constant rate, and so you can see the sound is moving out in all directions. It's moving that way, it's moving that way. Just like ripples on a pond, sound waves are going out in all directions. Well, what happens if this source starts to move? Okay. Well, then we're going to get something called the Doppler effect, and it's a change in frequency due to the relative motion between the observer and the source. So it doesn't just mean that the source has to move, it could also mean that you're running into these waves. And if we think about what happens, if you were running into these waves, you would reach these waves more often than they were actually being produced, which would mean the frequency went up in your ear, and that causes a change in pitch because we're hearing the waves occur more often than they normally do. So that's what I have down here. This is an animation of a wave being produced by a source in motion. You can see that source is moving to the right, and these waves out in front in the direction of the motion are getting squished together. They look like they're occurring more frequently. They aren't, but because the source is moving closer to those waves, they do sound and look more frequent. And then here, on the other side, since these waves are pulled away from each other as this source moves to the right, those waves get spread out. So if you're standing over here, you hear these high-pitched sounds because that's a high-frequency wave. But if you're standing over here, you hear a low-pitched sound because it's a low-frequency wave. So the Doppler effect, actually, you've all heard before if you've ever been at a railroad crossing as the train's coming by. As the horn blows as it goes by, it changes in pitch. It also gets louder as it gets closer, right? But it changes in pitch. It starts out high and gets low as the train whistle goes by. Okay, so the waves here moving apart, pitch decreases. Waves over here moving together, pitch pitch increases. Now this is the exact same thing as the redshift for stars. Remember, red is a longer wavelength than blue, so if a star is moving away from us, like if we're here and this star is moving away from us, then the light is going to shift towards a red wavelength, but if we're over here, light is going to shift towards a blue wavelength. So redshift and the Doppler effect, they're the same thing. Doppler effect in sound causes a pitch change. Doppler effect in light causes a color change. Okay. Last thing to talk about is interference in beats. If you've ever tuned an instrument, you know when you're getting close because you hear a loud, soft, loud, soft, loud, soft sound, and that's because the frequency of the two waves is relatively close. So sound waves interfere with each other, and that means they can interfere constructively or destructively. And if they have slightly different frequencies, then those frequencies are going to occasionally line up. The crest will occasionally line up, the rarefactions will occasionally line up, and then occasionally they'll misalign. And when they misalign, it gets quiet. When they align, it gets loud. And so we get this high or soft, loud sound that we call beats. Okay? And this little picture kind of shows us what's happening. So I have a wave up here that has a slightly different frequency than this wave down here. And right here they align at just the right instant so that they're completely out of phase, which is very destructive. Now as we move left, you can see that this crest and this trough, they're not quite perfectly misaligned, and that's because these wavelengths are slightly different because they have slightly different frequencies. And as we move further and further and further, right here, they're exactly in phase, and so we get a very loud sound here, very quiet sound here. And we can use the fact that waves interfere with each other to actually make headphones that can cancel each other out. So if we created a wave exactly the same frequency as this wave but shifted over half a wavelength, then we could get a just straight line, and that's noise canceling technology. There is one more thing to look at, and that's loudness. Now, loudness is something that's very subjective. The way we hear sound is different for everybody, and you guys are familiar with this if you've ever had a conversation with somebody and you feel like you're yelling and they can't hear what you're saying. As we age, our ability to detect sound also decreases. And so loudness refers to what we hear, and it's subjective. But it is related to the amplitude of the sound wave. If you're going to make your louder sound, you need to create a sound with a higher amplitude. That carries more energy. The problem is, since loudness is subjective, we don't have a measure of loudness. It's impossible to do that. But we can measure the energy moving through an area, and that's what intensity is. So a higher intensity sound should be louder, but not everybody's going to hear it at the same volume, the same loudness. And intensity is measured in decibels, which is a logarithmic unit, which means a change of 1 decibel is actually a multiplying change. It doesn't just add 1, it multiplies by a factor of 10. So 0 decibels is barely audible. 60 to 65 decibels, that's normal conversation level. And if you've ever shot a shotgun, that's about 165 decibels. And somewhere around 120 to 130 is a rock concert. And sustained noises at above 90 to 100 decibels can cause permanent hearing damage. You should wear hearing protection when you're shooting because these loud sounds can damage your ears.